different neutron number which will result in different mass number. So, for example, carbon, proton 6, neutron also 6, means C12, that is the normal carbon. But there are other carbons also, like there are what you call, sorry, there is C13 where proton is 6, neutron is 7, so total 13. So, the chemical properties of carbon C12 and 13 is same, but the mass number is different. So, the physical properties may vary. C12 and C13 physical properties vary. But the chemical properties are same, the reaction, everything will be same. Similarly, we have C14, proton 6, neutron 8, C14 is unstable. It can break down by itself. So, C14 is a radioactive carbon isotope. Please do not forget, C14, it is not stable because the proton neutron number is varying, okay, and radioactive carbon isotope. Similarly, isotope of hydrogen, normal hydrogen is 1 proton and 0 neutron, but if it has and of course 1 electron, no doubt regarding that, 1 electron, but hydrogen has an isotope called a deuterium, 1 proton and 1 neutron, of course 1 electron, it cannot change. If the electron number changes and proton number changes, it will not be the same element, then it will be a different element. And hydrogen also has another isotope, artificial one called tritium, 1 proton and 2 neutrons, of course 1 electron, that is tritium. Deuterium is a natural isotope. Deuterium is a natural isotope of hydrogen, naturally found, 1 in 7,000. Deuterium is to hydrogen is equal to 1 is to 7,000. That is the ratio which is found in nature. Tritium is an artificial isotope of hydrogen. In laboratory, in reactions, we can create. So, what is the mass number of tritium? 1 proton plus 2 neutron, that means 3. So, 1 H3, 1 H means 1 proton and total mass number is 3. Similarly, deuterium 1 H2 and normal hydrogen 1 H1. Anyway, so please remember, so what are isotopes? Different mass number because of different neutron number. So, similarly, in a bigger element like our uranium, proton number is 92, no problem, but different neutron numbers. A commonly found is neutron number of 146. So, uranium 238, proton 92, neutron 146. 238 is the most commonly found uranium. 99.3% of uranium in nature are this, but 0.7% uranium 235 is the proton 92, neutron 143, that is uranium 235. but we have other uranium also. These are both are natural. .3 and 0.7% is a naturally found, but we also have uranium 233, uranium 234. So that means proton is equal to 92, neutron is equal to 233 means 141. Here proton is equal to 92, neutron is equal to 142. So these are artificial isotopes of uranium. So coming back to our discussion, radioactive carbon isotope, I said, please understand, any element which can break down by itself, radioactive elements above lead 82 in the periodic table, all are radioactive, but beyond 92 plutonium onwards, these are artificial elements and its isotopes which can break down. That is the element and isotope business, please do not forget this. So coming to a nuclear reactor, and our discussion, most of them are related to nuclear fission and nuclear. So what is the reactor? Reactor is a device where controlled fission reaction take place. Nuclear reactor is a device where controlled fission reaction take place. Fission, nuclear fission, and the most commonly used element is uranium. Uranium 238 and uranium 235, they are commonly used for fission. Of course, then plutonium 239 and plutonium 240, these two isotopes are also used in the nuclear reaction. Uranium 238 and 235 naturally found, plutonium again 3940, which are used in the nuclear reactors. And so this, whatever fuel we use, the fuel which we use in a reactor is called fissile material. Okay. The nuclear fuel, fissile, fission, which can undergo fission, that is called fissile material. So uranium 238, uranium 235, plutonium, all we call it as fissile material, which can break down, which can be used as a fuel in the reactor. So in a reactor, we keep the fuel and please remember, in a reaction normally to radioactive elements can break down by itself, no problem, but to speed up the process, it may take its own time. To speed up the process, we may bombard it with fast moving neutrons. In a reactor, fast moving neutrons are used to speed up the process of breakdown of nuclei. Naturally, if you are waiting, it may take years together, maybe hundreds of years together to break down, but we need it in a controlled way, in a fast way. So we use fast moving neutrons for bombard it with fast moving the fuel and speed up the process of breakdown of the nuclei. So if if a fast moving neutron comes and hits a uranium 238, it may result in smaller nuclei plus free neutrons plus energy. So, if it is hit by uranium, it will result in smaller nuclei plus free neutrons plus energy is produced in a reactor. Smaller nuclei plus free neutrons plus energy is produced in a reactor. Now, just one more point, let me just add, in a reactor, to control the speed of these neutrons, okay, in a reactor, to control the speed of neutrons, we use moderators. Okay, we use moderators to moderate the speed. Similarly, just a second. So, in a traditional nuclear reactor, the moderators is used, they to slow down, okay, the moderators are used to slow down the speed of the fast moving neutrons, okay. And similarly, we also have then coolants. So, one good example of a moderator is a heavy water. Okay, heavy water can be used as a moderator. Heavy water is nothing but D2O, deuterium, the isotope of hydrogen. Okay, instead of normal water, heavy water can be used for better quality. Okay, so that is the concept of the nuclear. In a reactor, we use moderators, and we also what do you call then coolant. See, the energy, the heat energy which is produced, and when a reaction take place inside, a lot of energy is produced, or a lot of heat energy is released. So, you circulate water or a coolant surrounding we circulate coolant surrounding the reactor, coolants surrounding to absorb the heat. So, this coolant, it can be again heavy water can be a coolant, D2O, even normal water, that is light water. Since heavy water we are saying, so normal water is called light water. D2O, that is, and even liquid sodium is used as a coolant, even graphite can be used as a coolant. So, nuclear reactors have moderators, okay, one second. एक सेकंड So, control roads, okay. I just wanted to mention that particular word, I mean just somehow missed out. So, I am talking about fissile material once again. Then I talked about moderator, then I talked about coolant. Now, I am also talking about control roads. Control roads are those rods or elements which are used to control the number of neutrons. In a reactor, so that the reactor or the reaction in a reactor, if a reaction will not go out of control. Okay, that is called control road. See, for example, so it is also called poison. Okay, a control roads are also it is used as neutron poison. Control roads are also known as neutron poison. Okay. So, again graphite can be by this can be some of the example of control road: graphite, boron, boron is a good example of control road. So, coming back to my point, so in a reactor, okay, in a reactor, what is a reactor? Reactor is a device in which controlled fission reaction take place. So, we are talking about fissile material, that is the fuel, moderator, coolant, and then control road. So, four things, four different things I am talking about. Fissile material is the fuel, moderator is to moderate the speed of the neutrons, so that better better result, which can get the best result. Coolant to absorb the heat energy, that is why a reactor is running, okay, to absorb the heat energy produced. And control road, that is also called neutron poison, to control the number of neutrons, free moving or fast moving neutrons inside a reactor, so that the reaction will not go out of control. I am again telling you, just see uranium, I said proton 92, neutrons are 146 in uranium 238. So, when this is broken down into smaller nuclei and there will be lot of free neutrons flying around, these free neutrons can go and hit other uranium and again break it down, and it can ultimately result in a chain reaction. Ultimately it result in a chain reaction, and this chain reaction should be under control. So, we will remove and absorb some of the free neutrons. So, that is where we use control road. Please remember, one of the most infamous accidents which took place in the nuclear field was the Chernobyl accident in Ukraine in 1986. Okay, Chernobyl accident in Ukraine in 1986, and the Russian scientists, it was under USSR at that time, Chernobyl under USSR, now it is in the present day Ukraine, and in that the scientists were doing some experiments on control roads. They were doing experiments on control roads, they were withdrawing the control roads to increase the efficiency of the reactor. They were experimenting by withdrawing control roads to increase the efficiency of the reactor, and in the process the whole reaction, the reactor got out of control. So, they experimented with the control rod, they reduced the control rods, they allowed more free neutrons to fly around, and the whole reaction went out of. So, an uncontrolled chain reaction is nothing but it will look like a nuclear bomb. An uncontrolled chain reaction can result in the nuclear bomb. So, control roads, that is what went wrong. Okay. Anyway, so that is how about the reactor, broad things, I hope you got it. Now, coming to the nuclear technology and research and development in India. The most important, the primary research station is BARC, Bhabha Atomic Research Center. In Trombay, in Mumbai, okay. And this is the, and it is named after the Homi J. Bhabha. The pioneer nuclear scientist of India, who died in a plane crash while traveling to Vienna. He was going for an International Atomic Energy Agency meeting in 1969. In a plane crash, he died in Europe. So, he was the pioneer, and after him we named it as Bhabha Atomic Research Center, Trombay. This is the primary research center of India. This is where our nuclear the research reactors, most of the research reactors are located. This is where I will talking about that. This also the place where we are producing radioisotopes for normal use, for nuclear medicine. We are using radioisotopes in industry, we are using it in food processing, in agriculture, radioisotopes. So, isotopes of normal element like carbon, C14 is the radioisotope of carbon, please do not forget C14 is the radioisotope of carbon. So, we are conducting research on the radioisotopes for nuclear medicine, industry, food processing, etc., etc. Primary research reactors are located, radioisotopes are created here. Research on uranium based fuel for nuclear reactors. Uranium based fuel for nuclear reactors. It is also the place where our weapon research is going on. Weapon research is conducted here. This is also the research facility where nuclear waste management, we are conducting the nuclear waste management, and also we conduct the fuel reprocessing plants are located, waste management and also the nuclear fuel reprocessing plants. Nuclear fuel reprocessing plants are located here. Even BARC has also developed supercomputers called Anupam series. Supercomputers of Anupam series developed by BARC. So, a series of developments here. Now, just to clarify, so BARC is the primary center, the weapon program, the research on uranium fuel related, nuclear what you call radioactive isotopes of ordinary elements, for nuclear medicine, even gamma ray protection and all, for in the cancer treatments, a lot of activities. Now, there are two words which I would like to clarify for you. One is the enrichment and reprocessing. We have talked about this in polity, we have talked about it in international relations, many places I talked, but I am just in science I am repeating once again. Enrichment of uranium is the term we use, and another term is reprocessing of the fuel. See, enrichment of uranium means increasing the percentage of uranium-235. Increasing the percentage of uranium-235 in the natural uranium. Uranium-235 in natural uranium. See, I already said 238 is to uranium-235, this is the natural uranium, is equal to 99.3 is to 0.7. That is what is naturally found. But this cannot be directly used in a reactor for as a fissile material, cannot be used Okay, I was talking about BARC, Bhabha Atomic Research Center, Trombay. Homi J. Bhabha is our father of our nuclear program, we can safely say, and he died in a plane crash in 1969, I already said. And in BARC, we have the research centers, research reactors located, for research purpose reactors are located here. I will talk about them separately. Radioisotopes for nuclear medicine, industry, food processing, all are produced here. Uranium based fuel for nuclear reactors, uranium enrichment here, uranium based fuel, means uranium enrichment. Weapon research, nuclear waste management, nuclear fuel reprocessing, all are located here. Okay. And then of course, supercomputers are there, I said many things. Now, I am just making the difference between enrichment and reprocessing. Enrichment is the increasing the percentage of uranium 235 in natural uranium. The natural uranium is uranium 238 is to uranium 235, 99.3 is to 0.7, that is natural uranium. But it cannot be used in reactor directly as fissile material. So, we enrich it. So, what do? We enrich uranium, natural uranium, we enrich natural uranium, and depending upon the percentage we talk about different uranium. One is SEU, slightly enriched uranium. Slightly enriched uranium, this is where uranium 235 percentage increased from or between 0.7% to 2%. Okay. The rest uranium 238. Suppose uranium 235 is 1%, then uranium 238 is 99%. If uranium 235 is 2%, uranium 238 is 98%. So, that is called slightly enriched uranium. So, if it is the enrichment is between 0.7 and 2%, we call it as slightly enriched uranium. Then comes low enriched uranium. This is low enriched. Uranium 235% is between 2% to 20%. So, example, if uranium 235 is equal to 5%, then uranium 238 is equal to 95%. So, then it is called slightly low enriched uranium, slightly enriched uranium, then low enriched uranium. Now comes the third, HEU, highly enriched uranium. So, slightly enriched uranium in some of the reactors, like light water reactor, we will come to that. In light water reactors we use slightly enriched uranium. Low enriched uranium is normally used in pressurized heavy water reactors. Pressurized heavy water reactors, in some type of reactors we use pressurized low enriched uranium. Highly enriched uranium beyond 20%, it has application. So, it is uranium 235, 20% to 99%, and rest uranium 238. Highly enriched uranium is used in nuclear isotopes for producing some of the nuclear isotopes, and also it can be used in weapons. If it is a uranium based weapon, then HEU with uranium 235 above 95%, 95% plus. Highly enriched uranium, please listen carefully, if you are making weapon using uranium 235 or uranium based weapon, in uranium based weapon, then the U-235 should be more than 95%. Highly enriched uranium of that. See, even, so please remember, HEU can be even uranium 235, 30% is also HU only, but that is not sufficient to make weapon. Weapon require more than 95%. So, this is nothing but enriched uranium. Increase the percentage of uranium 235 which is naturally available in a weapon or in a quantity of uranium, then we call enriched uranium. Reprocessing of the fuel. Reprocessing of fuel is when a reaction is over in a reactor. When a reaction is over in a reactor, there will be lot of material or rather be lot of material left behind in the reactor. Lot of material left behind in the reactor, which we call it as spent fuel. So, what is spent fuel? What is left behind in a reactor after reaction is over, after fissile reaction is over or after fission reaction is over, what is left behind? After a fission reaction is over in a reactor, we call it as spent fuel. But this spent fuel, what is left behind? There are some useful compounds in that spent fuel. There are some useful compounds or elements. Say for example, after if enriched uranium is used, if enriched uranium is the fuel, there can be, right, there can be many elements and compounds left behind after the reaction. For example, there will be uranium oxide, uranium carbide, plutonium oxide, plutonium carbide, even many other compounds and elements will be there, which are very radioactive. Okay. After the enrichment, after the uranium is burnt completely, we may still get some uranium oxide, uranium carbide, plutonium oxide, plutonium carbide, or generally it is called mixed oxides, MOX. Mixed oxides from the reactor. So, when the reaction is over in the spent fuel, you will get many useful compounds like uranium oxide, carbide, plutonium oxide, plutonium carbide, or in generally we call MOX or mixed oxides, and the mechanism or the activity of segregating and taking out the useful, and plutonium, I said plutonium is not naturally found, it is found only in a reactor in a spent fuel. Plutonium, please remember plutonium 239 is a reactor grade plutonium, it can be used in a reactor. Subsequently, and plutonium 240 is a weapon grade plutonium. It can be reprocessed and made into weapon, atom bombs. Most of the present day atom bombs are made of plutonium 240. Plutonium is the fuel, uranium is not generally used because plutonium is more deadly, more effective. So, we can segregate plutonium 239, we can segregate 240, plutonium oxide, plutonium carbide, mixed oxides. This process of segregating and recovering the useful compounds from a spent fuel is known as reprocessing the fuel. The process of recovering useful compounds and elements from spent fuel is known as reprocessing of. I was talking about, please remember, reprocessing plants, reprocessing of or fuel reprocessing is known as fuel reprocessing. The process of recovering useful compounds and elements from spent fuel is known as fuel reprocessing. So, after reprocessing we can extract weapon grade plutonium. Most important thing is weapon grade plutonium, but it can be other also uranium oxide, uranium carbide, all can be used for various activities, but weapon grade plutonium you will get only through reprocessing. So, if you want to make atom bomb of high quality like using plutonium, you need a reactor first, then you need you should have spent fuel, and spent fuel can be reprocessed to get weapon grade plutonium. So, this process whereby you can create the weapon either through enrichment or through reprocessing. Enrichment of uranium or reprocessing and taking plutonium. This is what enrichment and reprocessing together we call it as ENR technology. I talked about this ENR technology at some point of time, you might have forgotten. Now, please understand, this is what enrichment and reprocessing. Enrichment and reprocessing, we call it as ENR technology. Enrichment and reprocessing. So, enrichment of uranium, uranium 235, increasing the percentage uranium 235, reprocessing, taking out plutonium 240. Both are deadly because both can result in the making of atom bombs. That is why ENR technology is considered to be a dual purpose technology. Both can be used for making weapons, dual purpose technology. Bhabha Atomic Research Center BARC has the capacity to do both enrichment and reprocessing. Both enrichment and reprocessing can be done in BARC. That is why BARC is considered to be the most important research center of India as far as the nuclear technology is concerned. And number 2 research center is IGCAR. मोदी जी को समझ में नहीं आया क्योंकि थोड़ा पढ़ना पड़ता है सब में, इनको पता नहीं होगा कि there is a center called Indira Gandhi Center for Atomic Research. अगर उनको इतना जानकारी मिल गया So, you will immediately rename it Madan Mohan Malviya Center for Atomic Research. मोदी जी का बच्चा नहीं है, नहीं है तो अपने बच्चों के नाम तो लिख ही लेता. Indira Gandhi Center for Atomic Research. We are in a spree to change the names, right? So, this is at Kalpakam in Tamil Nadu, almost 100 kilometers north of Chennai. Here, the main focus is on plutonium or rather fast breeder reactor research. Plutonium, uranium fuel research, uranium 233 research, I will come to that, fast breeder reactor research, uranium 233 is an artificial element, plutonium uranium fuel. Then they also have a research reactor here called Kalpakam Mini. Called Kamini reactor here, I will come to this Kalpakam Mini reactor, all research reactors. So, here uranium and also this uranium 233 can be ultimately extracted from thorium. So, thorium research in IGCAR, Indira Gandhi Center for Atomic Research, thorium research in IGCAR Chennai or rather at Kalpakam. So, it is very important center, the second most important facility after okay. HEU स्लाइड क्या था यार, तुम लोग अभी याद आ गया तुमको HEU. I said uranium 235 95% plus is highly enriched uranium, weapon grade. Okay. So, anyway, but anything HEU is anywhere between uranium 235 20% to 99% is highly enriched uranium only, but weapon grade, if you have to grade weapons, then it should be 95% plus. That is what I said. Anyway, so IGCAR number 2, very important facility. Then number 3, a third important facility, research facility in Indore called Raja Ramanna Center for Advanced Technology. Raja Ramanna Center for Advanced Technology, Indore. Raja Ramanna was another great scientist. He was even Science and Technology Minister and all in India at some point of time. It is in Indore. It is again, this is where research in laser technology, because this is very important in nuclear technology, in reprocessing and all, laser is important. So, Raja Ramanna Center, it pioneers research in laser. It also in accelerator, fast moving nuclear material. Accelerators, then high vacuum technology, cryogenics, then large magnets, so in laser technology, accelerators, because for fast moving neutrons, to create fast moving neutrons. Okay. Or it also have a research called synchrotron source, or rather I set up a synchrotron source facility. Okay, basically fast moving nuclear material, that is the concept of synchrotron. Okay. So, lot of even this Raja Ramanna Center for Advanced Technology, it is also collaborating with the Large Hadron Collider. It is an international project in Germany, France Germany border, Large Hadron Collider research. So, CAT is doing, Center for Advanced Technology is collaborating with Large Hadron, because India is a partner in the Large Hadron Collider experiments which are going on, and this has even helped in finding that Higgs boson particle, that is the element, the primary element which provide mass. Higgs boson particles, which ultimately result in creating mass. Okay. So, that is in Raja Ramanna Center for Atomic Research. They are collaborating with the Large Hadron Collider project which is going on in Europe, and it is a major center. Then another center is called Variable Energy Cyclotron Center, that is in Calcutta. Suraj is asking, is it necessary for a reactor to be near sea? It is not necessary, but if it is near sea, the advantage is the coolant and all, some of the nuclear waste, low level waste can be mixed with sea water. So, that disposal of low level radioactive waste is slightly easy to manage. Disposal of low level radioactive waste is easy. Okay. But it is not necessary that it should be along, but normally either on the river side or near the sea, that is what is generally done, so that we can, otherwise we have in Delhi, in Ghaziabad, we have a nuclear power reactor in Rawatbhatta in Kota, nuclear reactor there. So, these are not near the sea, but near the sea has some advantage, but it is not necessary. Now, the future nuclear reactors are coming up in Haryana, it is coming in Madhya Pradesh. So, no sea anywhere nearby, so it is not necessary. Okay. Anyway, so Variable Energy Cyclotron Center, Kolkata, VECC, Variable Energy Cyclotron Center. Again, it is providing fast moving nuclear particles for research in nuclear physics. Nuclear particles for research in nuclear particles, in nuclear physics, nuclear chemistry. Also, it produces radioisotopes. See, cyclotron is also where it spins very fast. You can the word when accelerator, cyclotron, these are all where the nuclear elements like proton, neutrons and all, they are spun, or rather they are allowed to spin at a very high speed. Fast moving neutrons and protons and all are created here, okay, using magnetism and all. Anyway, then so that is in Calcutta, and a fifth one is the Atomic Minerals Directorate. Atomic Minerals Directorate, this is for exploration and research, AMD, and it is located at Hyderabad. So, geological survey, exploration, prospecting, etc., etc. So, to get the atomic minerals, uranium, thorium, zirconium, atomic minerals are required. So, it is the responsibility of Atomic Minerals Directorate located in Hyderabad. Also, we have also developed a new one, a new facility after 2010, which during that time of the Prime Minister Manmohan Singh's time, Dr. Manmohan Singh's time, we have developed a new center called Global Center for Nuclear Energy Partnership. In Haryana, in just outskirts of Delhi, Bahadurgarh. In Jajjar district. So, this is the 6th research and development unit under Department of Atomic Energy. This is the 6th research and development unit under DAE. We have initiated in 2010 after a nuclear security summit. This facility was announced by Prime Minister at that time in the nuclear security summit held in Washington. Nuclear Security Summit held. So, here the design and development of systems or nuclear systems which are safe, secure and proliferation resistant. Safe, secure, proliferation resistant. And sustainable. So, it is a global facility to research, design and development of nuclear systems which are safe, secure, proliferation resistant and sustainable nuclear facilities or nuclear systems. To be created, and also to conduct global nuclear energy partnership. Global nuclear energy partnership. Nuclear security, very importantly, here we are concerned about nuclear security, meaning it should not fall in the hands of undesired elements. We are concerned about nuclear security. Nuclear security, see there are two things, nuclear security, nuclear safety. Safety is there should not be any leakage, there should not be any accident. Security is about the nuclear technology should not land in the hands of terrorists. Fuel or even instruments should not fall in the hands of terrorists, rogue states, or such states like Taliban. They may be running Afghanistan or North Korea, of course they have it, but our aim is this technology should not land in the hands of questionable governments. So that is what we talk in terms of nuclear security. So the research in nuclear security, nuclear safety of course, but main concern is security. Then radiation safety studies in Bahadurgarh, we are also global facility, we are talking about radiation safety studies, how far we can expose to radiation, etc., etc. So, in all other applications we would like to do. Okay. So, these are the 6 major research facilities in India, 6 major research facilities in India. So, I will stop here. Now, in the next class tomorrow,